Alright, welcome everyone. To today's video, we're going to be talking about exact and inexact differentials in this video, and then the next video we'll talk about changes in internal energy. Okay, so we talked previously about state functions and path dependent functions and path independent functions, right? State functions are path independent, okay, right? And what makes something a state function or path independent function is mathematically can be related to whether or not it has an exact or an inexact differential. Okay, so every state function has an exact differential, is path independent. Okay, right? And exact differentials are infinitesimal quantities which, when integrated, give path independent results. So kind of right, chicken and egg, right? The definition of these things are related with each other. We'll see through these set of slides here what exactly makes an exact differential. Okay. Right. Inexact differentials, right? When you integrate those things, right, it gives you a path-dependent result. Okay. Heat, work, examples of such. Right. So for our state functions, right, as we want to understand a little bit more about internal energy and enthalpy of the substance, okay, we're going to want to talk about their exact differentials. Okay, and so here we're just kind of trying to define what is an exact differential. Okay, and so we're going to be looking at, right, what is that mathematical definition before we hop into specifically talking about internal energy enthalpy. Okay. So let's consider some function f as a function of two variables. Okay, so call x and y, right? So we often we'll write f as f of x and y, right? To symbolize that f is a function of x and y, right? The total differential of f, so df, okay, can be written as such. Okay, it can be written as a sum of differential with respect to x and a small change with respect to y, right? And these things are then multiplied by the partial derivative of f with respect to x holding y constant, the partial derivative of f with respect to y holding x constant. Okay, and so this is the total differential of f. Right? If f is a state function, right, if it has an exact differential, okay, what must hold true is that this g of x, y here, and h of x, y, the derivative of one with respect to y has to equal the derivative of the other with respect to x, right? So as a reminder, right, this g of x is del f del x, and h of x is del f del y. Okay, so all this is saying, so this line here, right, which is saying that derivative of g with respect to y is equal to derivative of h with respect to x, right? And you can think of that as, you know, g with respect to y and h with respect to x, right? So you got to swap the dx and dy over, right? All this thing is saying is it's saying this, that dx of df dy equals d dy of df dx. Okay, that for this function, the order of the derivative does not matter. If I take the derivative of my function with respect to x and then y versus y and then x, I get the exact same thing. Okay, that makes a system. That means that function has an exact differential. That makes it a state function. Okay, so for example, if f of x and y is ax squared y, okay, I look at the differential of f, okay, I look at df dx, which is 2axy, and I look at df dy, which is ax squared y, okay. And then I'm going to take this term and take the derivative of it with respect to x. I'm going to take the term on the right, and I'm taking the derivative with respect to y. And when you do that, you get 2ax in both cases. So those equal. So f here is a state function, has an exact differential. Okay. Now, if you have something with exact differentials, okay, something is a state function, right, then you satisfy a lot of these different rules that we're going to use, okay, in other videos. So I'm going to just note here, right, that I'm going to be using some of these chain rules and cyclic rules and things like that, okay, in simplifying and solving certain differential equations and things like that in a little bit, right, in future videos, okay. And we'll do that in these videos to kind of derive certain relationships, but you do not need to do that yourself. Do not need to worry about what these different rules are, okay, but I'm presenting them here. I'm giving you here these different relationships between partial derivatives of a function, okay, of multiple variables. We're giving you these relationships in order to use later, right, when we talk about internal energy and enthalpy and things like that, okay? But again, you don't need to remember these, you don't need to memorize them, you don't even need to use them ever in this class. But we will use them when deriving certain things in the class.